Hi everyone, it's Mr. H here, and today we're going to get into the basics of special relativity. We're going to talk about time dilation, simultaneity, and length contraction. This stuff is really counterintuitive, and so I want to start off with something you may have heard about before, and that is the twin paradox. We have two twins, they're obviously the same age, and one twin decides, you know what, I'm going to go and become an astronaut. I'm going to go in a spaceship, and let's assume that spaceship is traveling at close to the speed of light, and I'm going to be gone for 10 years. So it's traveling at the speed c for 10 years. Well, when he gets back, what he's actually going to find is that his brother, who was on Earth, is really, really old. He's got a big, long, white beard and a hunched back, whereas he's only aged 10 years. His brother may have, who's remained on Earth, may have aged 40 years. And we're going to look at why that's the case in this video. Let's start off with assuming, just considering Adam and Betty in this picture. So here's a bus. It's going to be a really badly drawn bus. But here we have a bus with some wheels on it. And inside that bus is Adam. Here's Adam. Adam decides, while he's on this bus, that he is going to throw a ball at a speed v, straight forward. Betty is standing on the road outside the bus, and the bus is made completely of glass. And so what Betty sees is, depending on how fast the bus is moving and in which direction, she's going to see a different speed from the ball than Adam is going to see. In fact, if the bus is moving at 20 meters per second, and we're going to say it's moving at 20 meters per second in this direction, so via the bus is in this direction, then what that means is Betty is going to see the bus moving at 20 meters per second plus the ball moving at 10 meters per second. Now from Adam's perspective, if he's throwing the ball 10 meters per second straight forward, he's going to see the ball moving at 10 meters per second. But that is relative to Adam, or relative to the bus. From Betty's perspective, what she sees is she sees the bus moving at 20 meters per second and the ball moving at 10 meters per second as well. So the ball, from her perspective, looks like it's actually going to travel at 30 meters per second. That's relative to Betty, or the ground, or the rest, we could say. If I could get my pen working properly. Betty or rest. The key is relativity. And the question is this: don't light waves have to be relative to something? Like, if you think about it, we know water waves are relative to water and sound waves are relative to air. So don't we need something for light rays to propagate through? Well, we already know that we don't, but this was a huge hurdle for scientists for a long time. Maxwell had found the speed of light, but it was concluded by a whole bunch of scientists that it had to be relative to something. But what did it have to be relative to? They thought they had concluded, but they hadn't. It was the late 1800s that they were trying to look for something that they eventually called the ether. If you're at rest relative to the ether, it was thought that light would travel at the speed of light, c. If you're moving relative to the ether, it was thought that light would either speed up or slow down. So let me just give you an analogy here. Assume that the sun is here and you are looking at the sun and you are moving towards the sun at a very fast speed. Well, there's the speed of light coming from the sun, and then you're moving at a fast speed. And so what would be assumed is that you would actually have the speed of light moving faster here, because it's coming towards you and you're moving relative to it, and inside this ether that you're traveling through, that has to be faster. Now in the other case, if you were moving away from the sun, here's the sun shining again, you're moving this direction, and so the speed that you're going is not at the speed of light yet, but what it would seem like to you is it would seem like the speed of the sunlight is actually going slower. And so that's what they concluded, and that's what they thought they could conclude at that point, when indeed they couldn't conclude it, because it wasn't until Michelson and Morley came along that they actually proved them wrong in their assumptions. Michelson and Morley had a relatively simple setup, and what they did is they had a semi-transparent mirror. So what that meant is that some of the light was able to pass through that mirror and hit that mirror over here, and then back to the detector off of, when it came back, it hit like a reflective mirror surface. And then some of it was able to bounce off like a mirror and then pass through and refract through it as it comes back through. And so what they predicted is because these both have to go the same distance, so this light ray is going to have to go a certain distance, this light ray is going to have to go a certain distance. If we can change the speed that this light ray is going at relative to this light ray, then we should be able to see on this detector plate, we should be able to see that we're not always going to get a bright band of just the two light rays in phase. We should sometimes be able to see those two light rays out of phase, which is going to give us a dark band. So in other words, if we take the Earth and we set this up on Earth, here's our source coming in, and there's our detector down there. What we expect to see is, because the speed of the rotation of the Earth is not zero, but there's no rotation up and down, they would have expected that this beam right here, as it came back, would eventually at some point be out of phase. What they found from this orientation was that it wasn't out of phase, and so they just tilted it more and more, and they thought, okay, well, let's just find the right angle that it becomes out of phase. The problem was they were never able to do that, and that's because the speed of this light didn't change at all. In fact, they had to conclude that light traveled the same speed in all reference frames. So the light that was going up and down here was traveling at the same speed as the light that was going back and forth, even though you have the rotation of the Earth. Therefore, light travels at c in all frames of reference. And Einstein came along and he just adapted that very slightly. He said it's in all inertial frames of reference that we'll see later on here. So let's go back and consider Adam and Betty again. Betty is at absolute rest. And standing at absolute rest, if we were to release a photon of light on let's say a very simple clock, where that photon of light has to go reflect off of a mirror and come back down to the bottom, and that would be 1 second for Betty. So tick, tick, 1 second, tick, tick, 2 seconds. And that light has to travel straight up and straight back down. Now, in terms of Adam sitting on the bus, or standing on the bus, what he would also see is that light going straight up and straight back down in his reference frame. However, what Betty sees is much different. Relative to Betty, all right, let's be clear about this. That means this is relative to Betty. What she sees is the light traveling somewhat horizontally as well. She sees this photon not only traveling straight up, but it has to travel somewhat over at the same time. And so if you think about that, that means that the distance that this light ray has to travel is longer than the distance that this light ray would have to travel. Because that distance is longer, that must mean that a moving clock runs slower. Well, how much slower? Let's actually see how we would calculate this. I'm going to take this vector right here, and I'm going to just exaggerate it here. And what I'm going to do is I'm going to add the two components to it. We have the component of c, because speed of light that's moving upwards at, times ta, which is the time between ticks according to Adam. So from Adam's reference frame. And then TB, I'm going to have as the time between ticks from Betty's reference frame. So the horizontal component is the speed that the train is actually moving at, or the bus is moving at, times T from Betty, because she's the one that's viewing all this. Add the distance that Adam sees the light ray traveling at, plus the distance that Betty sees the bus move in that amount of time, and we get the distance that Betty sees total, because that's speed times time is distance. All right, so this is a measure of distance, this is a measure of distance, this is a measure of distance. Now notice again that Adam measures this distance because he's measuring it going straight up. Betty's measuring the distance it's traveled horizontally, and so overall the distance that Betty measures is c times the time that Betty measures, and that is not going to be a straight horizontal or straight vertical line. using Pythagorean theorem, what we can do is quite ingenious. And this is what famous Albert Einstein did about just over 100 years ago. He said, well, let's take this c times ta squared plus v times tb squared. And that's equal to c times tb squared. I'm just, the a squared plus b squared equals c squared. But now what I'm going to do is I'm just going to expand this out. So I'm going to get c squared times ta squared plus v squared times tb squared. And I'm going to continue expanding that out and get the following. And now what we're going to try to do is we're going to try to isolate tb. So we're going to try to isolate that right there. Now in order for us to do that, it's going to be simpler if we can just rearrange a couple things first. So I'm going to divide by c squared. And if I divide every term by c squared, what I'm left with is ta all squared plus v squared over c squared times tb all squared. And that's equal to tb squared. So now what I'm going to do is I'm going to get the tb's together, because I have a tb here and I have a tb here. I didn't mention that earlier, but there's two tb's in the equation. So getting me to that, I'm going to get tb squared minus v squared over c squared times tb squared. And that's equal to ta squared. Now I'm going to common factor out a tb squared. I'm going to get 1 minus v squared over c squared. And that's equal to ta squared. And now to rearrange that, I have to go ta squared divided by 1 minus v squared over c squared. So ta squared divided by 1 minus v squared over c squared. But then I need to take the square root of all of that to get tb by itself. Well, if I take the square root of all of that, if I square root the ta squared, that just becomes ta. And then I take the square root of the bottom, and I can leave that there as well. So the ta squared at the top, taking the square root gets rid of that, and we're left with ta divided by 1 minus v squared over c squared. What does that physically mean? Well, that means that tb, the temperature that the rest person sees, is equal, not the temperature, the time the rest person sees, is equal to the time that the moving person sees divided by 1 minus v squared over c squared, where v is the speed that they're actually moving at. And that's the equation that we have, just rearranged slightly here. So delta t naught is called the proper time, the time for the observer who sees the clock not moving. Delta t is called the dilated time. And so remember here that even though Betty is at rest, she is the dilated time because she sees the clock moving. So that's important to keep in mind. This is the equation that we have for time dilation. So let's look at an example together. Man, move the stupid thing. So here's our equation, and keep in mind that delta t is the person who sees the clock at rest. And delta t naught is the person who sees clock moving. All right, you already see the relative parts here. How much slower will Betty's clock run if Adam's speed is 0.25 the speed of light? So it's a quarter the speed of light. So that's the thing we're given. And then I'm going to ask you, assuming they're exactly the same age when Adam begins moving at that, who will turn 80 first? So let's go ahead and sub this in. So this factor is 1 over the square root of 1 minus 0.25c all squared divided by c squared times delta t naught. Notice here we're not actually solving for the amount of time that's passed. We're solving for this value right here, which, as I noted above, is sometimes labeled gamma. Now, for the purpose of this course, we're not going to use gamma, but oftentimes you'll see that just to simplify the equation. So what we get here is that the time of the clock at rest, so this is Adam's clock. Adam sees that clock at rest, and that is equal to 1 divided by, and the square root we get is 0.25c divided by c squared, which gives us 1 minus 0.0625. C squared divided by c squared, those are going to cancel out. and we do that, we get under the square root 0.9375. So 1 divided by the square root of 0.9375 delta t naught. And what we arrive at is an answer of 1.0328 delta t naught. Now, in terms of delta t naught being the time for Betty, and delta t being the time that Adam sees, just take a second and see, what does that mean? So hopefully, if you've thought about that or paused it, what you realize is that 1.0328 is the number of times slower that Adam's clock runs than Betty's clock. Because the light had to travel further, right? So it had to go slower. Runs 1.0328 times. And here's what that means. It means that when Betty's clock has gone over 1.0328 seconds, Adam's clock has only clicked one more second. So the second part of this question asked, assuming they're exactly the same age when Adam begins to move at that, who will turn 80 first? Well, because we know that Adam's clock is running slower, Adam's clock runs slower, then Adam will be the youngest. In other words, Betty will turn 80 first. So let's just think about this for a minute. If we were to travel to a distant galaxy close to the speed of light, what would happen is we would actually not age nearly as quickly as we would on Earth. So we could travel vast distances close to the speed of light, but that also brings in other problems into effect, particularly the fact that we would get very, very massive. And if we got very, very massive and we even hit a speck of dust in the universe, we would be kaput, unfortunately. So let's wrap this up with a couple ideas. The first is Einstein's two postulates. All physical laws must be equally valid in all inertial, non-accelerating frames of reference. And he also found that the speed of light through a vacuum, empty space, will be measured to be the same in all inertial frames of reference. Just to make that really clear, let's assume that you are in some type of car that is moving at the speed of light. And you are moving towards another car. Don't worry, you're in opposite lanes, so you're not going to hit each other. But you're moving towards another car, also moving at the speed of light towards you. That second, based on our everyday experience, if we were moving at 60 kilometers an hour and they were moving at 60 kilometers an hour, it would be as though we were moving at 120 kilometers an hour relative to the other person. In terms of c, this is where it gets wild. That's the speed limit of the universe, meaning that this car would see the other car moving at them not at 2c, but at c, whereas the other person would see the other car moving at them at c. It blows the brain because it's not something we experience in everyday life. However, we're going to see some applications of this that we do use on an everyday basis, and it will be quite surprising. The final conclusion for today is this: moving clocks run slower than stationary clocks. Moving clocks run slower than stationary clocks. And the other thing that we found from the Michelson Morley experiment is that light does not need a medium to travel through. There is no ether. Doesn't exist. All right, hope that's helpful. And as always, if you have any questions, feel free to reach out for help.